In today's video, we will discuss a variety of applications of quadratic equations. Before we consider specific examples, let's summarize the types of questions that we may encounter. Given the equation, we may be asked to evaluate for a specific output value. Or given the equation, we may be asked to solve for a specific input value. Given the equation, we might be asked to find the maximum or minimum output value attained. This value would correspond to the y-coordinate of the vertex of a parabola. Similarly, we might be asked to find the input value at which the maximum or minimum occurs. This would correspond to the x-coordinate of the vertex of a parabola. A harder kind of question might ask us to find the equation first and then answer any of the above questions. In our first example, we will consider a free-falling object. David tosses a ball upward from the top of a 96-foot building. The height s of the ball in feet above the ground t seconds after David releases it is given by the equation s equals negative 16t squared plus 80t plus 96. We are asked the following three questions. 1. At what time will the ball reach its maximum height? 2. What is the maximum height of the ball? And 3. At what time will the ball hit the ground? Let's think about a plan for answering these questions. The graph of the ball's height is a down parabola with domain t greater than or equal to 0. So the vertex of this parabola would correspond to a maximum value. The time the ball reaches its maximum height is the first coordinate of the vertex, and the maximum height achieved is the second coordinate of the vertex. So we can answer the first two questions by finding the vertex. The third question, when the ball hits the ground, its height is 0 feet above the ground. So we need to solve the equation s equals 0 for time t. Let's implement this plan and answer the questions. Since the graph is a down parabola, the vertex represents a maximum. The first coordinate of the vertex is given by t equals minus b over 2a, which simplifies to 2.5 seconds. So the ball reaches its maximum height 2.5 seconds after release. The second question can be answered by finding the second coordinate of the vertex. We find that by plugging t equal 2.5 into the formula. Thus, s equals negative 16 times 2.5 squared plus 80 times 2.5 plus 96, which equals 196 feet. So the maximum height the ball attains is 196 feet. Finally, the ball hits the ground when s equals 0. So we want to solve negative 16t squared plus 80t plus 96 equal to 0. We divide both sides of the equation by negative 16 to get t squared minus 5t minus 6 equals 0. This quadratic expression factors, giving us a product equal to 0. We set each of the factors equal to 0, and therefore t is 6 or t is negative 1. Since a negative time is extraneous in this problem situation, we conclude that the ball hits the ground t equals 6 seconds after being thrown. Let's consider a second example involving the area of a rectangle. Consider the rectangle with width 10 minus x and length x plus 3. First, write an equation for the area A of the rectangle. Second, find the value of x for which the rectangle has maximum area. And third, find the value of the maximal rectangular area. Let's again make a plan before jumping into the solution. First, note that the area of a rectangle is given by the formula area equals length times width. And second, if the graph of A is a down parabola, then the vertex will correspond to the maximum value. Now let's solve the problem. We have a rectangle with width W equal 10 minus x and length L equal x plus 3. Presumably, x is non-negative and less than or equal to 10, or we wouldn't have a rectangle. To answer the first question, area equals length times width, which is x plus 3 times 10 minus x, which after expansion and simplification is negative x squared plus 7x plus 30. So we have an equation for the area, and the graph of the area is a down parabola, so the vertex will correspond to a maximum. The first coordinate of the vertex is found by x equal negative b over 2a, which gives us 3.5 units. So the maximum rectangular area occurs when x is 3.5 units. The second coordinate of the vertex can be found by substituting 3.5 into the area formula. We get area is negative 3.5 squared plus 7 times 3.5 plus 30. So the maximum area is 42.25 square units. Let's consider a final example. The area of a rectangular playground is 600 square meters. The length is 10 meters longer than the width. Find the playground dimensions. We need to find the length and the width of the playground. Let's list what we know. We know 1, that the area is 600 square meters. We know the length is 10 plus the width, and we know the area of a rectangle is length times width. So now we can start to piece together a solution. We list what we know. We have area equal length times width, and we can substitute 10 plus W for L. Then we can distribute the W. So area is W squared plus 10W. Also, the area is 600. So substituting, we get W squared plus 10W equals 600. Now we can solve this equation for W, and we will know the width of the playground. Subtract 600 from both sides. Factor the quadratic expression to get a product equaling 0. Set each factor equal to 0. And W equals 20, or W equals negative 30. W equals negative 30 is extraneous since W represents a positive width in this problem. Therefore, the playground width is W equal 20 meters, and the length is L, 10 plus W, or 30 meters. These examples are by no means exclusive of all possible applications of quadratic equations, but they do give a reasonable indication of the types of questions that you might encounter.